Okay, we're going to be recording this part of the session. If anybody has any objections with recording, please say so now. Okay, so we're talking about the poles, zeros. We're talking about damping ratios, natural frequencies, etc. So I'm going to add something here to the Matlab code, and this is actually already in the original code that's in Blackboard, but I removed it for the example that we did last class. But I'm going to use a function that's called damp. And so what does the damp function do? Basically, the damp function is going to give me the dampening ratio of it's going to give me the dampening ratio of a transfer function according to a step input. Just a dampening ratio, I'm sorry. And I'm going to use another expression also that's called PZ map. Now, what does PZ map do? It gives me the pole zero map for the system. So it's basically going to tell me where the poles and zeros are. Okay. Now, let's look at the values that we had for the system. Let's play around with those and see the responses. So I'm going to run the simulation. I'm going to go here in order. I'm going to run the simulation first with the value of 1 that we had originally given. Okay. Oh, I didn't, wait a minute. I need to add here. I'm going to add both of those functions. I'm going to put a figure here. The only thing that figure does, the figure function, figure just when you're plotting things in Matlab, if you don't tell it to open a new window, it's going to overlap all of the plots on the same window it opens. So I'm already going to plot the step. I'm going to tell it to open a new figure, and then I'm going to use PZ map on the system. And I'm going to tell it to also please calculate the damping ratio and the natural frequency. I'm going to add those two. Okay. I'm going to run it. I'm going to first give it a value of 1. It's giving me, first off, I'm going to look at the pole zero map, and next up, we're going to look at so this is a response. Notice that the response is very slow. We had already seen this, okay? Click the stop share again. Click the stop share. There we go. We had already seen this response here. We had already seen it, and it was the very slow response. Notice that, first off, the antenna system that we are using, what order is this antenna system? Can somebody tell me? Oh, we can actually see it here in Matlab. What order is the antenna system? And order is like I'm talking about the mathematical order of the
third.
It's third order, correct, Daniel. It's third order because it's S to the 3. That means that if it's third order, we have to have 3 poles. Okay. Now, the only combinations I can have here are the 3 poles are real and different. The 3 poles might be the same and real, or 1 pole is real and the other 2 are imaginary. Those can only be the combinations I can have. So we have 3 poles there. If we go over here to the pole zero map, we notice that we've got the 3 poles here graphed. And what do we notice about the 3 poles? The only thing that's a bit I don't like about Matlab when they do this is that they Matlab plots it with these really tiny X's. But here's one, here's another one, and here's another one. What do we notice with what can you tell me of those 3 poles that we have there? What's the characteristic of the 3? Daniel, go ahead. Oh, I'm sorry, Daniel and then Marian.
Yeah, sorry.
No, it's fine. It's fine. You can go.
Okay, Marian.
I was going to say that they are real.
They're real, correct. They're real, That's why we have an exponential slow response. We don't have any oscillation because we don't have an imaginary part. The other characteristics is that they're all on the left-hand side. They're all negative. That's why the response is stable. Now let's look at the damping ratios, okay? And so if we go over here to Matlab and look at the damping ratio, notice that the damping ratio is very close to 1, okay? The dampening is very close to 1. If we go over here to what we were talking about, we can see that, sorry about that. All this is being recorded, the bloopers. We saw that a damping ratio that's 1 or close to 1 is called critically damped. And notice that we have it's critically damped and it's very close to 1. That's what we're seeing here. Okay. And that's why the response that we have is a response that's exponential. Okay. Now, what did we say about this response? It's too slow. It's too slow. We need for it to be quicker. And that's why we gave the system a higher K. So now let's see what happens when I give the system the K of 100. We had already seen that, but now let's look at the poles, the zeros, and the dampening. Now, what do we see in the pole 0 map? Move this. We've got one pole here, and we've got another pole here, and another pole here. And what do we see in the response? We see that the response has some oscillation. And why is that? Because we've got a real component. The real component is giving me the exponential decay here that we can kind of see here on the graph. And the imaginary component is giving me the oscillation that we're seeing in the graph. So the combination of the exponential and the oscillation is giving me this response. Now let's look at the damping relationships or the damping ratio. Notice that the damping ratio here is the dominant is close to 0.3, okay? We're a little bit below the value that we want, ideally, okay? We're a little bit below that. So we would like a 0.4, but notice that we're still getting a fast response, okay? So again, going back to Pablo's question, right now we have a 0.3 of damping ratio. We would like for that to be higher, a little bit higher, just so the system doesn't have so much overshoot and might be a little bit faster in its response. So let's see if we can modify that. Let's give it close these. Let's give it another value. Let's say we give it a value of, let's say 600. Okay, now we've got a quicker response that has some oscillation. We still have the poles here, and let's see what happened with the damping ratio. The damping ratio actually went down. So if we increase the gain, we're having less dampening. And notice that for this one, notice that the overshoot was higher. How do I usually interpret or try to remember the concept of dampening? Think about the overshoot and think that you have a hand here. I'm going to try to draw a hand. And imagine that the dampening is a factor that's making you push the signal down. Okay? So what happens when I increase the gain? I'm actually not generating more dampening. So the reference was 100, then I incremented it to 500. Let's give it a lower value, lower than 100. I'm going to say now that I'm going to give it a value of 70, of 80. And let's see what happens there. This is the pole zero map. And this is the response. That's very similar to the one we originally had. And the dampening right now is 0.36. Let's see if we can improve that. Now let's see if we can have, right now I gave it, I think, an 80. Let's give it a 60. By the way, there is an ideal value, and you're going to find that in lab exercise number 2. Don't worry about that. Just don't want to give a spoiler here. Oh, we've got less of an overshoot. We've still got approximately the same setting time. Let's see what happened there with the dampening. Now we've got a dampening of 0.4. Going back to your question, Pablo, do you notice that for the gain of 100, we had a dampening of 0.3, and we had an about almost a 40% overshoot, and the setting time was around, I think, 6 seconds or something like that, right? You see that? Then we went higher, and the overshoot went higher, and we don't want that. And the dampening was 0.1. Now we've got a dampening of 0.4, and notice that for a dampening of 0.4, we've got less of an overshoot. It's still around 20%, but the setting time wasn't affected that much. So we still have a pretty good setting time, okay? The setting time could be improved, but it didn't change drastically from the other ones. Now let's lower the value. Let's see if we can get an even, try to get an even better response. So what value did I give it?
It was 60.
60. Let's give it a.
Can we try 30?
Let's try 30. I think 30 is going to be, let's see, it's going to be a bit low, but let's see what happens there. Oh, another thing that we forgot to mention, well, look at this. Now we've got a smoother response with a lower setting time. The setting time is around the range, but we have a less overshoot that's less than 20%. What damping ratio do we have? We have very close to 0.6, okay? That very close to 0.6. So we're getting to a better value. That's why it's recommended usually between 0.4 and 0.8. Why is that? Because those are approximately the values that don't give you such a high overshoot. So you usually want to try to get to an overshoot that's less than maybe 18, certainly less than 20%. That would be roughly acceptable. So the dampening is going to give you that overshoot. Notice that as the dampening gets higher, we're basically pushing the signal down. And by pushing the signal down, we might be making it more slow. We might be doing that because there's a trade-off there. But we're certainly trying to improve the response. Moment. Okay. Okay, so is it questions with this one? Before
I have like another question.
Go ahead.
If the settling time, for example, it's actually kind of the same from like other examples we just saw, but like the transition, I think it's called.
The transient.
The transient is shorter. We prefer having a shorter transient over having a shorter settling time.
The answer to that, I'm sorry to have to give that answer, but it actually depends on the system.
On the system.
Yeah, because remember that we're talking about the antenna, this huge antenna. Maybe if you're tracking an object that's moving slowly, you really don't care if the antenna moves slowly as long as it's precise, right? But if you're trying to track an object that's quick, maybe you want a quicker reaction, even if you're going to sacrifice a little of the precision or overshoot. So it's always going to be a trade-off between one and the other. And actually, it kind of follows the exclusion principle. The closer you get to one parameter, the further you get from the other one, if you notice. So the lower the overshoot, the slower the system. The higher the overshoot, the quicker the response, or the quicker you get to the target value. So you're always going to be playing with those trade-offs. Okay, so it's going to depend on the type of response you want for that particular system. Usually one thing that again, that's why we talk about damping ratios between 0.4 and 0.8. So you usually wouldn't want an overshoot that's more than, again, 18. An overshoot of more than 20% might be problematic for large values. So you're usually working in that range.
Okay.
Okay. And if you really don't care that the system is slow, as long as you want precision, then basically you're looking for an overdamped response.
Overdamped or one?
Overdamped,
or it doesn't matter.
It could be overdamped or critically damped. It's a slow response. That the characteristic with these three is that there is no overshoot. So for critically damped, no dampening or overdamped, you're not going to go over the desired value. That's why it's exponentially trying to get there. It's going to be slower, but you're never going to go past the value. Okay. So I don't know, maybe you're thinking of, you're talking about a robotic arm that's going to do a drilling operation and you want it to reach the position precisely, even if it's slow. Okay. And that's when you look at these types of response. Okay. The underdamped responses are going to be, the underdamped responses are going to be quicker responses. And that's when usually you look between these values here. Okay. If for some reason, now let's reason this out. Do you all notice that the values for the damping ratio are all positive, right? And I just said that the damping ratio was equivalent to me trying to push. So the damping ratio is trying to push the response down. That's what dampening means. So a positive dampening ratio is pushing things down. What happens if somehow you get a dampening ratio that's negative? What would that mean? What do you think that would mean? A negative dampening ratio.
It might like worsen the system.
Definitely.
It's gonna like push it. Like
it's going, instead of pushing it down, it's pulling it up. So let's see what happens. Let's look at that. Let's go over here to our antenna system. And what was the breaking value that we gave it in the previous example? What was the value that we gave it that was really nasty? I think it was Marianne mentioned 10K, and I think 10K.
1,000 and 10K was the one that make it unstable.
Yeah, let's give it the 10,000. Well, let's give it 7,000. It's large, but it's less than the 10. And let's see what happens there. Well, it's one of the weird responses. Notice the response. What do you notice? What do we notice in the polls for this? This is an unstable response. We had already said that because it's oscillating. Pablo, go ahead.
The two imaginary poles are on the right side of the plane.
Yeah, we've got imaginary poles here on the right-hand side, and imaginary means oscillation. So if the imaginary poles are on the right-hand side, that means that the oscillation is going to get larger. So this is unstable, and it coincides with the pole zero map. Now let's look at the dampening for this case. The dampening is, oh, the Zoom controls, this is being recorded, and Zoom, if you're listening to me, then I don't care. The Zoom controls are so bothersome. They are not user-friendly where you place them if you're sharing your screen. Look at the dampening ratio. The dampening ratio is negative. Why? Because instead of pushing the signal down, it's making it larger. So a dampening ratio that's negative, as I think Luis said, it's going to generate a response that I don't want. It's going to generate a negative type of response that's going to, by default, be unstable. Now, notice one thing here that nobody's asked about. We've got 3 poles here because it's a third order system, and we're being given 3 values of dampening and actually 3 values of frequency. So what's up with that? Because the examples I gave were examples of a second order system, but a purely second order system. This is a third order system. Well, what happens if the system is third order, fourth order, fifth order, or larger order? There's going to be more than 2 poles. However, there are going to be poles that are going to be called dominant poles. And those are the poles that are going to, let's say it this way, those are the poles that are going to dominate the system response. So in this case, even though we have one real pole that's negative, that would give me a stable response with a dampening ratio that's positive and a certain natural frequency, this pole isn't the one that's dominating. The poles that are dominating are the ones that are imaginary and are on the right-hand side. If I have any poles on the right-hand side, those are always going to, I'm sorry, those are always going to dominate. Okay. Questions up to this point? Okay. Basically, lab exercise number 1 that you guys are going to start working on Monday, basically lab exercise number 1 is this. It's for the 3 different configurations of the antenna. Give it different values of K to see the different responses and analyze and interpret them, okay? With regards to the pole zero map, the dampening, and the natural frequency. That's basically what it's about. The next thing that we're going to see after that is, okay, wait a minute, but I want the antenna to behave a certain way. I want it to reach no more than 20%, and I want the response to be this way. How can I do that? Well, there are procedures and control systems where we can define the value of K that we want for the system behavior. And also we can find the ranges of K that are going to determine the stability of the system. Going back to Josue's question. And there's a couple of mathematical methods to do that, and we're going to see those next up. Okay. Questions with this this part here that we're talking about now?
No.
Nope.
Okay. Good.